This is a short introduction to our work on super-resolution reconstruction for diffusion MRI. In diffusion MRI, there is an inherent trade-off between the spatial resolution, the acquisition time, and the SNR of your images. Our question was, is it possible to improve this trade-off? Can we have a higher spatial resolution without having to elongate our acquisition time and without having a low SNR? So we went to look at super-resolution reconstruction. In super-resolution reconstruction, they acquire a set of low-resolution images, and from those low-resolution images, they estimate a high-resolution image. Up until recently, in diffusion MRI, they did exactly the same thing. They repeated this process for each diffusion gradient direction. So for each diffusion gradient direction, they would acquire a set of low-resolution diffusion-weighted images and estimate a high-resolution diffusion-weighted image for each of those diffusion gradient directions. Then from these high-resolution diffusion-weighted images, they would estimate their high-resolution parameters. However, we're not interested in those high-resolution diffusion-weighted images. No one cares about them. They're only interested in their high-resolution diffusion parameters. So we were thinking, why not just skip a step and why not directly estimate our high-resolution diffusion parameters out of our low-resolution diffusion-weighted images? This means we can incorporate a diffusion model into our super-resolution reconstruction, and we now use all the information we acquired to estimate our high-resolution diffusion parameters. Furthermore, this also means we can now do a motion correction with B-matrix rotation. Now we can, before they had to acquire the same set of diffusion gradient directions for each slice orientation, well, now we can play with those diffusion gradient directions and we can have an optimal Q-space sampling and that motion correction with B-matrix rotation. So how are we going to acquire our low-resolution diffusion-weighted images? Well, it is important that each low-resolution image contains complementary information on the high-resolution object and thus samples a different part of K-space. So we're going to acquire our low-resolution images with a high in-plane resolution and a low through-plane resolution, so with thick slices. So the idea of super-resolution reconstruction is that you only improve the slice thickness, so only improve the resolution in one direction. So now, when each low-resolution image is acquired with its different slice orientation, and we rotate our slice orientation and we look at K-space, then we see that each image will sample a different part of K-space, because a rotation in image space equals a rotation in K-space. So that's how we acquire those high frequencies, which are important to get a high spatial resolution in diffusion MRI and in MRI. So now we have our images, we know how to acquire them, we got our low resolution images. Now, how are we going to get those high resolution diffusion parameters out of this? Well, we're going to use a forward model. This forward model explains how to get a multi-slice low-resolution image out of high-resolution DTI parameters. So we know that to go to an image from our DTI parameters, we use the DTI model. So that's our first step. Then we also know there is motion, because there's always motion. Your patients will always move, so that can be modeled and estimated and put into a motion parameters. Then we also have a geometric transformation, because that will explain us how we acquired our slice orientation. We also have a downsampling, because we acquired a certain voxel size and also as well as those thick slices. And then at the end we also have a certain blur, because we truncate our K-space and also our slice selection is not perfect. This results in a set of nonlinear equations, so it becomes a nonlinear regularized least square problem, which is then solved using a truss region Newton method. So it becomes an iterative process where the high resolution parameters, diffusion parameters, are estimated out of our low resolution images. Now, if we look at some results, here you see an FA map. Each time the FA map is sampled on a 1.5 by 1.5 by 1.5 millimeter grid. But they are estimated from different sets of diffusion-weighted images with a different resolution, and the right one, of course, with using super-resolution reconstruction. If we compare our super-resolution DTI FA map with a regular high-resolution FA map, we see the same small details, but they are no longer concealed into noise, because the diffusion-weighted images had a higher SNR. Moreover, if we compare it with a low-resolution FA map, we see that the partial volume effects are less in our super-resolution DTI FA map, so that we actually can see those small structures and they're not blurred away. So in conclusion, we can say that with super-resolution DTI, you can enhance your resolution while preserving a high SNR and a low scan time. It incorporates the diffusion model, so it means we can have an optimal Q-space sampling, and we can also include a motion correction with the corresponding B-matrix rotation.